So the question in problem 6 is to determine if U is in the subspace of R4 generated by V1, V2, V3. So the question here is determine, we want to say, is U in the span of V1, V2, and V3? That's what we're being asked. An equivalent version, if we want to ask in terms of vector equation, we're saying, is U a linear combination of V1, V2, and V3? Is U a linear combination of V1, V2, and V3? This is equivalent to asking, is the vector equation C1V1 plus C2V2 plus C3V3 equals U consistent? All asking the same thing. And I didn't even write down the original question. Determine if U is in the subspace of R4 generated by these three vectors. That's equivalent to all three of these questions. So the way we'll answer this question is to use, move our column space and null space. The way we're going to answer this question is to look at the augmented matrix for this vector equation. So I'm going to set up an augmented matrix with 1, -3, 2, 3 in the first column, and then 4, -4, 5, 7 in the second column, then 5, -3, 6, 5 is the third column. I'm going to remind myself this is the augmented matrix, and put -1, -7, -1, 2 in the fourth column. And find the reduced row echelon form. So I'll do the hard parts. I know those first two aren't multiples of each other, so I can just write down those first two columns. But now I got to figure out the rest. So I've got 1, 4, 5, -1. 1, 4, 5, -1. Close that row, open the next row. -3, -4, -3, -7. Close that row, open the next row. 2, 5, 6, -1. Close the row, open the next one. 3, 7, 5, 2. Close the row, close the matrix, close the command. Double check. 1, 4, 5, -1. -3, -4, -3, -7. 2, 5, 6, -1. 3, 7, 5, 2. So we end up with the identity matrix. So the reduced echelon form we see there's a pivot in every column. More importantly, there's a pivot in the rightmost column of the augmented matrix. Therefore, the equation is not consistent. Therefore, U is not a linear combination of these three vectors. So U is not in the span of these three vectors. So U is not in the subspace of R4 generated by those three vectors. So the augmented matrix has a pivot in its rightmost column. Therefore, U is not in the subspace of R4 generated by V1, V2, and V3. So that's how we answer the question. Notice that this is no different than how we were asked at the kinds of questions we were being asked before. So going back to the top, the column space of A is a subspace of Rm because A has m rows. So all the columns of A are in Rm. The solution set to Ax equals 0, if A is m by n, the vectors x have to be in Rn because A has n columns, and the number of columns of A must equal the number of rows of B for AB to be defined. So in this case, we see that the augmented matrix has a pivot in the rightmost column. Remember, we only invoke the rightmost column when we were talking about an augmented matrix, and we always point out that when we're talking about an augmented matrix, we say the augmented matrix has a pivot in the rightmost column. Therefore, U is not a linear, the vector equation is, this vector equation is inconsistent, and that means that U is not a linear combination of these three vectors, and that means U is not in the span of those vectors, all equivalent questions. If we think about R4 is a four-dimensional space. We can think about breaking up R4 into subspaces. What we have is the span of these three vectors. Notice that V1, V2, and V3 are all linearly independent. So the span of those three vectors, V1, V2, V3, is a three-dimensional subspace of R4. So if it's a four-dimensional space and the span of these three vectors takes up three of them, there's one left that is, so there's like a line going through R4 that is not part of the span of these three vectors. So it's important to start thinking about what's in and what's out in your total space. We have a three-dimensional subspace of R4. That's the span by these three vectors. And then we have the fourth dimension of R4 is this line spanned by the vector U, because U is not in the span of those three vectors. Any other questions in section 2.8? Remember that the trick is not just answering the question that's in front of you, but thinking about all the other questions that are possibly attached to that. Any other questions in section 2.8? Well, I'll switch pages. 28. Okay, let's see what we've got in 28. So 28, we want to construct a 3x3 matrix A and a vector B such that B is not in the column space of A. So A is a 3x3 matrix, 3x3 matrix A. And vector B such that B is not in the column space of A. So I got to build a matrix A and a vector B such that, and B can't be in the column space of A. So we're given a piece of information about A. Tell me something about A that's going to have to be true. What's something about A that must be true so that we find a vector that's not in its column space? So I got a linear combination of the columns of A, and I'm missing this vector. What does that tell you about the column, about the matrix A? What's linearly? A can't be linearly dependent. A is a matrix. What's linearly dependent? The columns of A must be linearly dependent. How come? Why is that? How is that going to help us? That's partially correct. We're going to have to write columns of A that are linearly dependent. Non-trivial solution to what? Non-trivial solution just never kind of stands on its own as a justification for things. You're on the right track, but you're saying that the columns of A are linearly dependent, so therefore there's a non-trivial solution to what? There's always something that has to go along with that. R3 is not an equation. There's no solutions to R3. Non-trivial solution to, what's the rest of that sentence? The columns of a matrix A are linearly dependent. The matrix does not have any solutions. AX equals 0. The homogeneous equation has a non-trivial solution. Why does that matter in this case? If the columns of A are linearly, independent, how does that mean that there's a vector that's not in the column space? In this case, you're right, but you're right because we have an additional piece of information that you have not cited yet. Right now, your explanation is not sufficient. You're saying things that are true, but you're missing a piece of information that makes what you're saying the same as what I need you to say. I'm looking for a vector B that is not in the column space of A. And you've told me about that the columns of A are linearly dependent. They are going to be in this case, but that still hasn't gotten us to what we're looking at. A is a matrix, and so it doesn't have a span. We don't talk about the span of A is going to be a bunch of multiples of the matrix A. We're going to have to make the equation AX equal B inconsistent. That's what it means when B is not in the column space of A. AX equals B is going to have to be, we're going to look for a B such that AX equals B is inconsistent. So does it matter if the columns of A are linearly independent in general? Is that what makes a matrix equation inconsistent? That's what we need. A doesn't have a pivot in each row. Since A is square, that will also mean that A does not have a pivot in each column, but that is not sufficient to get us through in this case unless we point out that A is in fact square. So the key thing that we want to recognize here is that if B is not in the column space of A, that means B is not a linear combination. B is not a linear combination of the columns of A. That's equivalent to saying that AX equals B is inconsistent. We're looking for a vector B such that AX equals B is inconsistent. And now we can say that means that A does not have a pivot in each row. That's the key thing that we need. We need to say that A does not have a pivot in each row. Since A is square, A will also not have a pivot in each column, but that's not what got us to where we need to be. It is also the case that since A is square, A will also not have a pivot in each column, but that doesn't matter unless we specifically use that information to point out that since A is square, A does not have a pivot in each row. This is the thing that we need. This is the thing that we need. It's only equivalent to the columns of A being linearly dependent because A is square. So since A is square, A also does not have a pivot in each column. Since A is square, A also does not have a pivot in each column. Since A is 3 by 3, A is square, A also does not have a pivot in each column, and the columns of A are linearly dependent. But that's not relevant, and that's not what we're going for. That's not relevant to what's going on here. If you walked into court and said the columns of A are linearly independent or linearly dependent, therefore here's a vector B that's not in the column space of A, you would lose that case. And it doesn't matter if you're right. So it's because A does not have if B is not in the column space of A, that is, B is not a linear combination of the columns of A. That means the equation AX equals B is inconsistent. We just have to construct a matrix A that does not have a pivot in each row. So I'm going to say A is not going to have a pivot in each row. So 1, 0, 0, 0, 1, 0. And then I just need something that's not a pivot. So 1, 1, 0. When in doubt, always make your life easy as possible. And then B can be 0, 0, 1. The important thing to realize here is that we needed to construct a 3 by 3 matrix A that did not have a pivot in each row. And then find a vector B that was not in the span of the columns of A. Now AX equal B will be inconsistent because B is clearly not a linear combination of the columns of A. And that's what we were looking for. Any questions? Like I said before, like I say many times, it's not about answering the question in front of you. It's about answering everything that could be related to that question in front of you. Why solve one problem when you can solve 5 problems? Any questions on 28? Any other questions in 2.8? How's everybody okay? In problem 14, find a non-zero vector in the null space of A and a non-zero vector in the column space of A. So we have this matrix A. It's this 3 by 4 matrix. So as in 11. So 2, 8, 11. A is this 3 by 4 matrix. 3, negative 9, negative 3, negative 9, 9. 2, negative 4, 2. 1, 1, negative 5. Negative 5, 7, 1. And we want to find, 14 refers to 12. Dang. So in 12, the matrix A is this 5 by 3 matrix. 1, 4, negative 5, 2, 3. 2, 5, negative 1, 7, 3. 2, 5, negative 1, 7, 3. And 3, 7, 0, 11, 4. 3, 7, 0, 11, 4. So A is this 5 by 3 matrix. So that means the column space of A is in R5 and the null space of A will be in R3. We're going to find, one of the things that we need is to find the reduced to echelon form of this matrix. And the reason, one of the things, the problems that we run into is that our calculator will not reduce, I can't remember if this is over square or under square, but if I just plug this matrix into my calculator, because my calculator is dumb, I have to plug in the wrong one so you can see that. So negative 5, negative 1, 0, and then 2, 7, 11. And right now I'm like, talk to the problem writer for this set, and I'm like, oh, dude, it did not have to be this big to get your point across. Okay, so what happens, you got 1, 2, 3, 4, 5, 7, -5, -1, 0, 2, 7, 11, 3, 3, 4. Your calculator is like, well, I can't find the reduced echelon. It's an invalid dimension. It is not an invalid dimension. Your calculator is just dumb. It's really annoying. So if you go back, if you go back, if you just put in a couple of columns of zeros to square out the matrix, then you'll be able to find the reduced echelon form. So I'm just going to go in here. If I insert a couple of zeros, I'm just going to insert 2 columns of zeros. They won't have any effect on the first 3 columns. But it will allow us to find the reduced echelon form. Just ignore those 2 columns of zeros. This is just a workaround because I guess in Texas they don't like tall matrices in Texas. They don't mind if they're wide, but they don't want to be tall. Not in Texas. I don't know why that is. But we want the reduced echelon form of the matrix. And we get 1, 0, 0, 0, 0, 0, 1, 0, 0, 0. And it looks like -1/3 and 5/6. Yep, -1/3 and 5/6, and then 0. So we see that the first 2 columns are the pivot columns, and then the third column is a combination of the previous 2. So I can't even remember what the question was. So the column space of A is in R5 because A is 5 by 3. The null space of A is in R3, 5/3. Thank you. The null space of A is in R3 because A is 5 by 3. So a basis for the column space of A, we could just pull these first 2 vectors. So if we want a basis for the column space of A, note that I'm not just saying column space of A equals. I'm not just saying column space of A equals, because I'm about to write down just 2 vectors. I'm writing a basis for the column space of A. So I'm going to write a set of vectors. The first vector in a basis is going to be 1, 4, -5, 2, 3. And the second vector in the basis is going to be 2, 5, -1, 7, 3. There's a basis for the column space of A. That's supposed to be a 7. It's not right to say column space of A is these 2 vectors, because the column space of A has an infinite number of vectors in it, not just 2. It's also not right to say this is a basis for A. That doesn't mean anything. A is not a vector space, A is a matrix. The column space of A is a subspace. Because what you're going to be doing is you're going to try to type as little as possible because it's a math class and you're not going to want to write full sentences or whole phrases. And so you're just going to be like all casual. Column space of A is these 2 vectors. It's like, that's not what I asked for. Tell me that's a basis. All right. What was the question? 14 was find a non-zero vector in the column space of A and the null space of A. Here, 1, 4, -5, 2, 3 is a non-zero vector in the column space of A. That's the easiest thing to do. Just pick out one of the columns of A. In the second part, for the null space, to get the null space of a matrix, we have to write down the solution set to the homogeneous equation. So I'm going to bring my matrix back up here. I'm going to write down a solution set. So this is going to be x1 x2, and x3. So x1 times this column plus x2 this column, and x3 this column. So I'm going to say solve for the basic vectors in terms, solve for the basic variables in terms of the free variables, and this isn't going to fit. We're just going to have to use our memories. So my solution set, there's three variables. So x1 is going to be 1/3 x3. x2 is going to be -5/3 x3, and x3 is free. So x will look like x3 times the vector 1/3, -5/3, and 1. If we don't like writing these, if we don't like writing the fractions, we can also say this is the same thing as just some other x3. I can also use, say, 1, -5, 3. If I just multiply the whole thing by 3, now I've got nice integers and everything's cool. You could say that the column space of A is equal to the span of that set of vectors. And if I ask for a basis, then I'm going to assume that what you're giving me is an attempt at a linearly independent set. All right, so x3 times 1, -5, 3. This is a basis for the null space of A. Basis for null space of A. It's going to be one vector in R3, 1, -5, 3. And there it is. So if you want a non-zero vector in the null space of A, there's one. 1, -5, 3. Any questions? How's everybody? Why would because the third column is not that linear combination of the first two. 1 + 2 is equal to 3, but 4 and 5 is not equal to 7. And 5 - 1 is not 0. Any questions? If you look in 2.811, the column space of A is in R3, and the null space of A is in R4. It was weird not having an answer written up there, just like this matrix, and then we moved on. Like, here's a matrix. Let's do something else. Any questions? How's everybody? I know I brought in basis, and there weren't any questions here about basis, but that's where things are headed. We're just taking small steps, but that's where things are headed. We got to do big picture stuff. All right, any other questions in section 2.8? How's everybody? The reason that they had to say find a non-zero vector in the null space and a non-zero vector in the column space is that since the null space and the column space are both vector spaces, if it just said find a vector in the null space, 0 is a vector in the null space because 0 is a vector in every space. Same thing column space. 0 is a vector in the column space. All right. Any other questions in section 2.8? Yep, write the solution set to the homogeneous equation in parametric vector form, and then pull those vectors into a basis, and to make it a set, and just list them, and then say, this is a basis for the null space of A. So related to the previous question, you could also describe this by saying that the null space of A is the span of the vector 1, -5, 3. You could also write it that way, because now you're telling me that it's all the multiples of this vector. Any questions? Usually what will happen here is that if you wrote the third vector, if you just took these three vectors and wrote three vectors here and said column space of A is the span of those three vectors, then I have to cross the third one out and I said find a basis. Then and on a piece of paper I would have circled said find a basis. But now I'm just going to write in as a comment on your quiz or test, in all caps, find a basis. Any other questions in section 2.8? All right, let's pause the video on homework 2.8 and we'll move on to homework 2.9.